All right, so let's start. I have remembered to start the screencast, and it's running. So, reminder, homework is due tonight, along with your grading. You probably remember. And then questions. I know there are people with questions, so let's ask them. For example, you just said you had a question.
Just on a homework one.
Okay, what is it?
I was asking for the correct way to write to output a file.
Okay, to output a file.
I mean for question 4.
Mm-hmm.
So I guess I can show the code.
I guess like print stream, but
yeah, with open, I try to call it.
Yep.
File.
Okay, you want to know how to use the. Okay, cool. So what you just said, stream. You can use the with command, or you can do something that's a little more straightforward, which I'll just show you really quickly. So I'm just going to show you very quickly a simple way in which to open a file and write something to it. Okay? Use the command open. And what you do is you say open, you give the name of the file, my file, and then afterwards you can give either W if you want to write to the file, deleting anything that's in the file already, or you can put an A, which means append to the file, not deleting stuff that's already there. You can also leave that blank or put an R if you want to just read the file. And what you get back is an object, let's call it F, which represents that file. And if you print it out, it's an open file. It's like a handle to a file. It then has various methods, such as, by using tab, I see that there's a read method and a write method. If you do f.write and give a string as input, it will write that string to the file. It might not immediately appear in the file if you look at the file, unless you close the file or you flush the output stream. It buffers the output, so the very moment that you write it isn't necessarily written to the file. It's an important optimization, since if you're writing lots of little characters, you don't want to actually write them all so that they're in the file instantly. So just to give you a very simple example, if you take this and you say f.write hi, then if you look in the file, probably, but not guaranteed, you'll see that hi is in the file. Let me check. Say, I guess I can just look here, look in the file. Notice the hi is not in the file. So that is not a bug. That's not incorrect behavior. The reason, again, is because of buffering. So if I then go back here and I go flush, so I say f.flush, that means flush the output stream, and now it should be in the file. And there it is. You can see a little tiny hi at the top. As an aside, I want to point out that in SageMath Cloud, when you open a file, if that file changes on disk, then the changes will automatically be reflected in the editor. Okay, so just so you know. That's why the hi appeared when we have this. We didn't have to close the file and reopen it or anything like that. And the automatically, currently I think it checks to see if the file's changed once every 5 seconds. So it should instead be using some event-driven thing to check, but I wrote the code, it didn't seem to work robustly, so I just stuck with check every 5 seconds from now. Okay, and then after you make a file, one thing you can do is close the file, and then now it's closed, everything gets flushed when you close it, and it's now safe to open it from another program, etc. There's also a with statement, which I haven't talked about very much, but you were just showing me an example where you open a file using with. This is nice just because it's extremely straightforward, and you should be able to understand how to do this well. To answer your question in gory detail? Okay. So this is how you read and write files. Yes?
Sorry, on that, I was just kind of running the code as you wrote it as well. I did f.write, just hi, and
yes.
then when I flushed it, it
yes.
actually had a red dot before the hi. Is there something that I didn't know?
Wait, a red dot?
I ran f.write hi 3 times.
Okay.
Or did it 3 times, and then did f.flush, and
yes.
it appeared in my file.
Yes.
Oh, no, it didn't. Sorry. There were 3 red dots, and then 3 instances of hi.
Huh. Maybe, I don't know. Sounds exciting.
Yeah.
You're seeing red dots.
I could just be hallucinating.
Yeah. Yeah. Maybe there's a problem with your computer. I don't know. Stuck pixels. Okay. So other questions? Okay. So the agenda for today, we're going to finish up talking about Python classes, or at least finish what we were talking about. So on Wednesday, we made a Python class that represents a rational number, and I promised that we would also make a Python class that represents the rational numbers, i.e. the field of all rational numbers, that single infinite object. And that's what we'll do first, and then we'll talk a little bit more about decorators. In about 1 second, I said some basics about decorators last time, but I want to give you some extremely sophisticated, complicated decorators that are included in Sage, show you some examples of how decorators are really useful in practice. Some of these are complicated and some aren't, but they're often very useful to know about. And if we have time left, which I doubt we will, then I'll show you some examples of graphics in Sage. Okay, any questions before we proceed? All right, let's go. So, first quick review. Let's look at the code that we wrote last time, which is in a file rational.sage. So this is a class that models a rational number. An instance of this class, it is, in quotes, a rational number. So we think of it as being a rational number. And remember, we wrote an init method around line 8. And it takes a numerator and denominator as input. It normalizes them in the form that we chose, which is completely up to us, but is a typical way to choose to normalize a rational number. It's nice because given a rational number, there's exactly one representation of it as a quotient that satisfies the conditions. Namely, the numerator and denominator are co-prime, and the denominator is positive. We wrote a repr method. This one is kind of an ugly method because, or it looks kind of ugly because even if we make the rational number 5, it'll print out as 5/1, which is kind of annoying. I didn't fix it, but if you wanted to fix it, you just do a little if statement there. You'd say if self.d equals 1, return, string of self.n, otherwise do this. So just change it slightly. Then we wrote an add method that adds a rational number to another number, and it had a type check in it. If the other number isn't a rational number, then it gives an error, otherwise it does the addition. And I think this is in the file rational.sage. In the worksheet that we were using before, we actually implemented a multiply method and I think a negation method and so on, which I didn't copy over here. So I just wanted to quickly review that. Now let's think about another step, which is to implement a class that represents the collection of all rational numbers, which I'll call the RationalField. That'll be the name of the class. Okay, so what we just did was make something that represents a specific rational number, but at least to us as mathematicians, there's another object out there that we might want to model, which is the collection of all rational numbers, which is often denoted by Q. Let's say Q for quotient, right? Because rational numbers are quotients. Quotient starts with a Q. So here, I'll turn the light on for a moment. So the rational numbers, it's just this big set, and it contains 0 and 1 and 1/2 and -3/5, 22/7. This pin's terrible. Better one. 8/3, etc. Okay, so that's the, well, yeah, there's a lot of other things in it. It's infinite. So it's a big infinite set, but it's completely sensible, I think, to make a class called RationalField, and an instance of this class is the RationalField. And you typically only want to ever have one instance of this class. And then you start thinking about, maybe there's methods that you'd want to have that are associated to the rational numbers. Like you might want to have a test to decide whether or not something's in here. You might, it might be nice to have a function that tells you, that would enumerate the rational numbers. That is, you could do something like, you could write code like this, for a in whatever you're going to call your rational numbers, called Q, and then print a. Obviously, this would be would take a long time, but it would be nice if there were a way to represent this in Python so that it would systematically enumerate rational numbers in a way that's guaranteed to hit any particular one. So, and it turns out there are very interesting algorithms that efficiently enumerate the rational numbers. In the sense that they give you each rational number exactly once, and they don't involve computing GCDs and so on. There's some Conway enumeration that does that. So there's lots of algorithms that you might actually want to use here. And then you start worrying about things like, what if I want to make matrices that have rational entries? How do I specify that I'm only considering matrices with rational entries? Well, it's kind of handy to have an object that's the rational numbers, because then you can give that as input to something else and specify, say, matrices with rational entries. Okay, and you could also, let's see, what else could you do? It's sort of obvious what kind of methods you want to implement for a specific rational number, like addition, multiplication, subtraction. For the collection of all rational numbers, they're more subtle. And they turn out to be, the methods turn out to be, maybe in the rational numbers they're somewhat obvious, but then there's other similar objects where it's a bunch of numbers that you can multiply and add. And you might ask questions about what is its cardinality. In this case, the rational numbers is infinite, but there are other similar types of objects called finite fields that come up a lot in engineering and cryptography, and they're finite, as the name finite field suggests. So like one is called fp, which is the numbers from 0 up through p minus 1. And then if you created a class that represents this, it would have a method which is, please tell me what the cardinality is. Okay, so let's try to make a rational number class. It's not going to do very much, but it'll do something at least. So you switch to half one again. So we'll make an init method. There's no additional data needed. There's just one field of all rational numbers. So it'll just do nothing. By the way, you probably have never seen a Python function that doesn't have something inside of it. And in fact, syntactically, it's kind of like you can't do that. It's a syntax error if I just do, I don't know, if I just kind of try to put nothing in there. So this could frustrate you if you ever have to do it. So I need to put something else, but this should not work. Look, expected an indented block. You actually have to give the indented block up there. So that's kind of annoying. It turns out that there's a keyword in Python specifically for doing absolutely nothing so that you can put something in there, and it's called pass. So look. So we do absolutely nothing. But now that makes it syntactically valid, and we can evaluate the code. And now we can make our rational numbers. So I can say q equals rational field, and I can print it out, and there we are. So it seems kind of silly, but this idea does allow you to organize a lot of ideas or a lot of constructions in a nice, clean way. Let's try to think of some methods. Cardinality, that'll return how big it is. And I mean, let's just be silly. Really, really big. But there's, of course, more precise ways to say that. Another one is, as I mentioned, is enumeration. So it turns out there's another dunder method for enumerating through an object. And it's called dunder iter, I-T-E-R. It allows you to iterate through an object. What it is it's a method that you define, and it's supposed to give back elements of the object in such a way that you get every single thing in the object at a given point. Even if the object's infinite, you won't get everything at some finite point in time, but any particular element should appear. I'll implement an incorrect version of this as follows. Let's see. This takes some explanation. I need to explain what this yield thing is, which I'll do in a moment. I probably should add one to I. Okay, this is completely wrong, but watch. If I make the rational field, I can now do for n in q, print n, I'm going to just say I want it to actually stop iterating through the rationals at some point. Otherwise, it's just going to go on forever. And so I've put a break statement in. So what that code does is it sets j equal to 0. Then it does for n in this infinite set, the rational numbers. What it'll do is it'll set n equal to the first rational number, the second rational number, etc., according to some enumeration, which was actually incorrect in my code up there. And it'll print out that rational number. And then if it happens to have done this more than 10 times, it'll just break out and stop doing this. So let's run it and see that it actually worked. Woohoo! The main problem, though, is that this is incorrect. I haven't ever mentioned the yield statement before. So it's pretty amazing, but you can write a function that returns something that when you iterate over doesn't terminate. It's a kind of, I don't know, a clever construction that you can do in Python and various other languages. And instead of putting return, you put yield. You can do this with any function. You can define any function anywhere, and instead of putting return, you put yield. And what that does is it gives you some sort of thing in Python called a closure that will return when you iterate over it, it'll keep giving you back the things that are yielded. So, and this does end up getting used a lot in various places that aren't necessarily about iterating over infinite sets. But if you want to iterate over some object, often it's a really clean way of expressing what you're doing, because you have, instead of building up some very large list or something, you can just write code in a nice natural way and at some point yield the next thing. And then you have something else that calls that thing and starts iterating through it. And then at the moment when it stops iterating through, for example, it breaks out of the loop, it does no further work. It just stops doing that iteration. So, I mean, this may sound kind of rude and abstract, but the entire amount of code to fully implement and illustrate what I'm talking about is on the screen right now. It's only like 7 or 8 lines of code total. And it's allowing us to iterate over some big object. One problem here, of course, is that it's kind of stupid because this isn't going to give us a correct iteration over all rational numbers, because that's not the right algorithm. We need a more clever algorithm to do this. There is a more clever algorithm in Sage, by the way. Sage has its own field object called the rational numbers, or RationalField. And if you do the same code but over that, you'll see it's going to give us a genuine looking iteration. So this really is iterating over the rational numbers in some way that will eventually hit any particular rational number. Okay. And by the way, I'll print out a few more of them. By putting a comma at the end of the print statement, it will not insert a new line. So you can see, like, here are the first 1,000 rational numbers according to the enumeration of rational numbers that happens to be coded in the RationalField class. So can anybody think of anything, any method we might want to add to our RationalField? So wow, that's a lot of, I'm going to delete the output there. Okay, can anybody think of any method to add? Yes, I should make it a singleton. Because right now you can make multiple copies of this class, and that's kind of stupid because really you only need to have one. It gets kind of, there's various recipes for doing that. And I think basically you make some sort of base class that represents being unique, and then you'd make this derived from that. But there's a number of different ways to do that. Another way is you make a function that returns an instance of this class, and then you always call that rather than directly creating an instance of this class. And what you do is when you make that function, if you've never created this thing before, then you create it the first time, and then ever after you always return the cached version. So there are a number of different ways to make this a singleton. And in Sage, we have some way that involves deriving from some base class, and it's got ridiculously complicated over the years. So, but yes, you would want to do that. But can anybody think of a method to add? And there's an easy way to cheat to think of some inspiration because there is a rational field in Sage already. We could just look at it. How about let's make it so that we can construct rational numbers using this. So there's another method, which I haven't showed you yet either, called call. And what it does is, well, let's see, call it with an N and a D. So what it does is it makes it so that when you have an instance of your class, then, so I'll say Q equals rational field. Then if I use parentheses and I call, then it will call that method. So basically, just like dunder add allows you to override plus, dunder call allows you to override the parentheses, the function call notation for instances of your class. And throughout Sage, the way that you construct an element, or one of the standard ways to make an element of a big infinite object like this, of a ring or a field or whatever, is you call that object with certain sort of input. So in this case, 2, 3. So it would be natural to, instead of saying print n and d, we could actually return a rational number. So do return rational number n comma d. For this code to work, I need to load rational.sage, which was that code I defined yesterday or Wednesday. Okay, so now when we call rational field, we're going to get back the rational numbers we made before. See? And just to confirm that these are the annoying rational numbers we made before, for example, notice that it prints and it has both the numerator and denominator because we didn't implement a nicer print method. So that's another nice thing to do with the rationals. Okay, let's look at qq-.tab because I can't really think of. So there's cardinality, which we already did. Oh, here's one that turns out to be useful. Yeah, of course, this is an obvious one. Random element. So an algorithm that, I mean, there's lots of algorithms for producing random elements of the rational numbers with various properties. And a good place to put these algorithms, if you're building a massive program that's a million lines of code, might be as methods of the rational field, right? I mean, can you think of it? Give me an algorithm that would give you a random rational number, where by random I mean chosen with respect to some distribution, but there's many different distributions. So if you just give me anything at all, it would define some distribution. What could you do if you wanted to make up a random rational number? Yep.
Just get a random numerator and a random denominator.
Yep. And if the denominator is 0, then choose again. Yep. So that would make a random rational number. Of course, then you have to figure out what you mean by a random numerator, because are you going to choose between 0 and 10? Are you going to choose between, I mean, what are you going to choose? So there's a lot of ways to choose a random integer. And if it's just completely random with nothing else, then what distribution do you want to put on the integers? And of course, being able to choose random numbers, so just illustrating this with our, look, it's 9. Why is it 9? What if I do it again? What am I going to get? Doesn't seem like a very good random number generator because there's no denominators. Oh, wait, there's one. So be able to get these random numbers associated to the rational numbers or any other similar field, I'm going to write the word field, is very, very important when you're developing code and testing things. Because it's useful to be able to generate lots of random numbers. So if you're going to maybe implement algorithms or use algorithms that involve computing with matrices over the rational numbers, it would be handy if you could generate lots of rational numbers at random, and hence you could generate matrices at random. In Sage, there is a little bit of code for generating random numbers in the rationals. If we do double question mark, we'll probably see something. Memory serves me correctly, it's a really boring small subset of what should really be there. So this is the source code of random element in the rational numbers. I'll zoom in. So apparently what it does is it takes, there are some parameters like bounds on the numerator or denominator, which may or may not be given. It then constructs random integers, possibly passing in these other parameters or not. And in a sense, it reduces to whatever the integers can do regarding generating random elements. So if you want to know what the options are, you really have to look at the integers. And then when you look at the integers, you find that there's, you can give parameters so it'll uniformly choose them in an interval. And then one of my grad students made up some funny distribution on the integers, which allows, arbitrarily large integers to appear, but usually gives you small integers, which is often useful for testing, and made that the default. An interesting project that somebody could do would be to look in the literature, brainstorm, ask people, try to come up with some ideas for various ways of choosing integers at random. Like what sort of distributions on the collection of all integers might be interesting and useful besides just uniform distribution on some interval and then this other weird one that my student made up. And then come up with a couple of others, name them, and then add them to the random element function of the integers. So that's a project idea. Because I think it's kind of boring how few distributions we have. We have lots of, there's lots and lots of standard distributions like the normal distribution and so on when you're doing, when you're considering floating point numbers and some interval, or at least just when you're doing statistics, there's tons of interesting distributions. But when you think about choosing integers at random and so on, I don't know. It turns out to be really important in kind of pure math applications like this, but it's sort of irrelevant in statistics. But a funny thing is, if you do this, I don't know, I've done this sort of thing a lot. Like you say, oh, give me a random matrix over the rationals. It calls the random element method with some parameters, and they're pretty stupid. Apparently, it's just making them uniform between -2 and 2. The people get pretty annoyed when they see that, actually. They prefer to have a better default choice of random and also more flexibility for what the random elements are. In any case, that's another method that you might have on the field of rational numbers, make a random element. And there's a lot of others that are not immediately coming to my mind, but if we do qq.tab, we'll see. Let's see, there's things like, a lot of these things are kind of silly. The rational numbers are a specific type of field, and there's lots of other fields for which there's interesting questions you can ask about them, all of which pretty much have the answer 1 for the rational numbers, or 0. And so they're kind of boring, but a lot of the words right there are asking questions about the rational numbers or about a general field or ring, which are kind of trivial to answer in the case of the rational numbers, but possibly very, very difficult to answer for other similar objects. So then you start, what ends up happening when you implement a big system is you implement the rational numbers, you don't even bother writing functions to answer those trivial questions. You only answer the questions in the more complicated cases. Then people write code that uses either the rational numbers or a more complicated object, and their code gets all broken when they use the simple rational numbers because you didn't provide all the methods uniformly. So you end up deciding, I better have all the methods, all the questions that you might ask about any field available for the rational numbers. But then it gets kind of daunting because now when you look at the questions you can ask about the rational numbers, there's a huge number of different questions, and it's just completely overwhelming. So do you really care about the 0 ideal of the rational numbers? Probably not. But you can ask for it, and you get back something. Okay, so let's just quickly review. This is our class RationalField. There's a class in Sage similar to this that's probably thousands of lines of code, and it has a lot of answers to questions that are kind of trivial for the rational numbers, but for uniformity, they're there. But some of the algorithms that you find in RationalField, such as iterating through all the rational numbers, getting random elements to the rational numbers, are pretty subtle and could be potentially much, much more complicated than they are now. Okay? Oh, one other thing you'd want to implement, or that is implemented in Sage for the rational numbers, is how do you typeset it so it looks pretty in tech, for example? Because you want it to be the case that when you do, for example, show of the field of rational numbers, it should, whoa, that sucks. Yeah, that's not so good. I wonder why it doesn't. Well, it should be a nice bold Q, but apparently MathJax doesn't properly typeset that. So I don't know why that is. That's a bug. Okay, so that completes talking about making this class, unless there are any questions. All right, so let's talk a little bit about decorators. So I told you very briefly last time what Python decorators are, and since it's so simple, I'll just say yet again exactly what happens. So if you write @foo def f of anything and then you put something here, then that is the same as def f of blah, 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 f equals foo of f. Oops. So that's decorators in a few lines. However, the amazing thing is this idea is incredibly useful. You can have a whole bunch of, you can stack the decorators. Like you could put @foo and @bar, that sort of thing. And typically what you call the decorator could be something like, please log all of my inputs and outputs. Please cache my inputs so that if you call the function with the same inputs again, it doesn't have to recompute everything. It'll just use the cached value. I'll show you that one in a second. So it's an incredibly useful construction, even though, honestly, it looks really, really simple. I remember when I started using Python, there were no decorators, and there was a lot of discussion on the list trying to figure out what sort of syntax to use and lots of different proposals. There's something called PEPs, Python Enhancement Proposals, and this PEP. So there's hundreds of these, and each time a new feature is proposed for Python, a PEP is written, and there's a PEP, this several pages of text, which goes through the various options for how you might do this sort of thing, and then they discuss the pros and cons of each one, and at the end, Guido van Rosen, the author of Python, or the guy that started the project, decides on one of them. This is the one he chose, and one of the main reasons is it makes very clear what your intent is right at the top. So it's really meant, the design is meant to be read rather than written. If you're just writing, you might like the bottom one better. You define the function, then you do something. So it kind of fits the flow of writing. But with code, you're much more likely to be reading it than writing it, especially with Python. That basically decides a lot of the design choices with Python. It's designed to be easy to read rather than easy to write, although it is pretty easy to write usually. But unlike programs in certain other languages, like C++, you can often dive into a Python project that's maybe hundreds of thousands of lines of code and actually figure out what's going on. Just because it's pretty hard to really obfuscate things. Things are usually pretty explicit. With C++, it can be extraordinarily difficult because of the C preprocessor and multiple inheritance and templated classes and so on. There's a lot of features in C++ that can result in incredibly hard to understand code. I don't know, do you guys program in C++ at all? Who here programs in C++? You do. Have you ever found code difficult to read? Yeah, always. So, okay, avoid C++ if you can. I've programmed in it a lot. It's powerful, but it's good in like little pieces, but bad in big pieces. Okay, so that's it. That's all it is. So you should think decorators are ridiculously easy. The only thing that's hard is, well, I mean, foo could be really complicated, right? It's an arbitrary Python call. So it could be, foo could do 1 million lines of code on F. So therefore, decorators can be very complicated. But it's not the idea of a decorator that's complicated. It's just what the decorator does could be arbitrarily complicated. All right, so let me show you a few decorators in practice. Let's see, cached function. This is a good one. So let's say you make a function f. See, a good one is actually Fibonacci numbers. So let's see. So let's see, if n is bigger than or equal to 2, gosh, I'm putting this all wrong. Return fib of, why am I, you guys did this as one of your homework problems. Actually, let me make an artificial thing that's clearer about what's going on. I'm going to call this function stupid, and what it does is it sleeps, so it'll simply wait for 2 seconds, and then it'll return n times n. So basically, it gets an input, and it goes, then it returns the answer. And actually, just to make that clear, let's make it go, and then we want to make sure we actually see the so it's thinking, and then it'll give us back the answer. So like you might have to do that too if you're trying to square 17. And there it is. Okay? So it would be nice because this function takes so long to evaluate if we could really, really easily make it so that when you call it again, it instantly knows the answer and doesn't have to do any work. And we like to do that in a way that doesn't mess, like, it'd be nice to not have to rewrite the inside of the function. And as you guessed, let's use a decorator. So I'll just take this, put it down here, and there's a decorator called cached function. There's also cached method for caching a method of a class. Functions, when they're inside of a class, are called methods. Okay, so now we've made another function, also called stupid, which will behave identically the first time we call it, as far as we can tell. However, look what happens if we call it again. Whew. So it just instantly gives us back the answer. It doesn't do the call at all. So to recap, this is an example of a useful decorator. You can stick it on top of any function you're writing wherever, and what it does is it remembers the input to the function and the corresponding output. And if you call the function with the same input, it will give you back that output instantly. If your function depends on something like the size of a file or something else out external, then this may not be what you want, because if you call it with the same inputs, it's just going to instantly give you back the output it gave last time. That's all. Also, if you're going to call this function a large number of times, every single time you call it, it remembers what it was called with. And that memory has to be somewhere. And so, in fact, it could cause you to run out of memory if the output were very big, for example, or the input. So there are some caveats with using cached function. But there are a lot of situations where it's really useful to speed up your code. Exactly this thing, cached function and cached method, is used very extensively in Sage, where it will remember difficult calculations so that when you do them again, they're fast during that session. But that can also, as I mentioned, lead to memory loss in the sense that, and you might think it's a memory leak. Oh, I called this and now suddenly I have less memory. But it's not a memory leak. It's intentionally remembering the answer from a previous call. Actually, well, it's hard to illustrate that because there's a command get memory usage which tells you how much memory is used. I don't know if we're going to be using enough memory doing this for it to even register. We'll see. I wouldn't be surprised if it's, yeah. It's the same. The reason's because you have to use quite a bit of memory for it to even register. The thing is that Python manages its own heap, and this is only going to tell you when there's additional allocations. So we would have to do something. If we were to make it so this function returns something really big, then we would notice the memory usage going up each time we call the function because it's caching its answer. Okay, so that's an example. Here's another one, which is pretty scary. It's exactly the same, except it caches stuff on disk. So it creates a file for each input. And that's nice because even if you completely quit this, you kill the whole project server, whatever, you still have the result on disk. I think it probably takes some sort of file name or something, or directory name. Let me see. Yeah, you have to pass it in a directory. Okay, so let's do that. Okay, and now when I call this stupid function with some number, it'll take 2 seconds the first time, but the next time it'll be instantaneous, or nearly instantaneous. And if we look at the file system, there's now a file corresponding to that particular input. That number there is some hash of the input. So it creates one file for, well, actually it creates two files for every single input to your function. So if you're going to call your function, 50 times, and it takes like 10 minutes to do each calculation, this is really, really good. Because once you call the function, the next time you call it, it's instantaneous. It just loads the answer from disk. If you're like Robert Miller, who was one of my first PhD students, and you write a function to check something about elliptic curves, and you're going to call it millions and millions of times, maybe 10,000 times per second or something, and your file system happens to be an NFS, network file system, you could cause a lot of pain to all other users of the system. So this is a network file system that has the property that every time you create a file, there's a little bit of overhead, and that overhead may be noticed by other users of the system. So he used this disk cached function thing for a while, and suddenly everybody in the system's like wondering, why is the whole computer so slow? And it turned out after a week we figured out that he was writing millions and millions of files to some directory. So, and there are standard Python libraries that do this sort of thing as well, where they will cache a function call to a file on disk. In SageMath Cloud, when I was migrating from one format to another, I discovered a user that had about 10 million files in their project. And I was just taking an enormous amount of time to copy them all. And it turned out they were using a similar caching system. You should probably not use files on the file system if you're going to cache like 10 million things. For that, a much better choice is to use SQLite, which is extremely easy to use from Python. And I'll write the word SQLite right here. Don't do the above millions of times. Use SQLite. And the way you use it is just to import SQLite 3, and then you read the documentation for the SQLite 3 module that's standard in Python. This will create a single file on disk. It's a relational database, and you can store stuff in it. There should be a disk cache method that actually uses SQLite, but I don't think anyone wrote one. Project idea. That would be a really good thing to add if it isn't there already. Simon, SQLite's easy to use in Python, right?
Yeah, I just learned how to use it last time. It's very straightforward.
Okay, here's another one that's neat. Interact. It's another decorator. So watch this. Let's say I have a function. Let's see. Let's think. What's a good function? How about one that, I don't know. I'm not very creative at the moment. It'll take, blank piece of paper. Okay, it'll take two numbers and it will multiply them together. I'm going back to elementary school. It does print %s times %s equals %s. And then I play around with it, so I call it with various inputs. Whoa. Oh, I forgot to put the answer. So I can call it with various inputs, and then it's pretty neat, and I show it to my, my 8-year-old buddy, and he tries to use it, but he's having a lot of trouble typing the numbers in and hitting Shift-Enter, and it's kind of annoying. So wouldn't it be nice if we could just turn it into something with little sliders or buttons or something like that? And so there's, or at least like something that's more user-friendly. So there's a decorator called Interact, and you just stick it above a function, and what it does is it generates, when it evaluates the function, it generates a user interface for using the function. Notice there's an error. Don't worry about that for a minute. You have to give, or it's recommended to give default values, and there's ways in which the default values for the parameters get turned into buttons or sliders. So if you give, for example, the list of numbers from 1 to 12 and the list of numbers from 1 to 12, then what it does is it will make a little drop down for each of those parameters. So you can make that one 7, you can make that one 10. Whoops, I guess I missed 9. If you, instead of using square brackets, if you give an iterator, it'll give you a slider. So let's say we want to go from 1 to 100. and then it'll, oh, I forgot the parentheses, sorry. So it gives us back a slider, which you can then drag and let go, and you get the corresponding value. So that's nice. And there's actually a shocking range of different controls like that. If you do interact question mark, you can see them. There's things like color selectors. There's a whole bunch of different things that you can do. You can make little matrices that you type entries into, et cetera, et cetera. So yeah, let's say you could do C equals and color red, and then I don't know what we're going to do with the color. I'll just do something stupid. Just print it out for now. But so, you know, you'd select the values of N and M, but then you can click here and select a color, which right now is just printing out the RGB color. So that's another nice application of a decorator. You just have a normal function. You can still call this function in other places with N, M, and C, but if you, right when you evaluate it, it gives you this way of sort of playing around with the various inputs to the function in a way that is kind of more user-friendly.
What happens if you pass
If you passed what?
a number, you see?
Instead of generating a color control, it'll generate a blank.
I mean, if you had the control for the color,
Oh,
does that change anything?
when you say pass a number and you mean call it later on, it won't do anything. It'll just, I mean, it'll just print out that number. So if I do f of 3, 4, 17, what? It could be that there's a bug. Call takes exactly, huh. Maybe we change the semantics actually, because, oh yeah. Okay. In the Sage notebook, not the Sage Math Cloud, when you use interact, it would create this output and it would leave the original function unchanged. However, in Sage Math Cloud, things are a little bit different. To make things more powerful, you can do some cool things like the f that you get back is actually a little more complicated. So look, you notice what just happened? When f gets decorated with this interact, you can actually set attributes of f, and that changes the controls. So keep your eye on the m slider. I'm going to set f.m to 50, and suddenly the thing moved. Okay. If I do f.n equals 4, then that thing changed. And probably if I do f.c equals green, maybe the thing will change from red to green. So you can change things here that impact what's here. So you can have multiple interacts, and they can change each other this way. So you can have one changing values in another. You can also have the code inside of an interact create another interact. So you can have nested interacts. All right, I'm going to give you 30 seconds of graphics stuff. There's a bunch of graphics in Sage, but there's also, whoops, I just want to show you one thing very quickly. There's the Matplotlib gallery right here. So this is a large collection of plots that you can draw using Matplotlib. Matplotlib plotting works very much like in MATLAB, but of course it's Python code. But if you just kind of take any example here, like this pie chart. So that looks pretty neat. And then you can see here's the code to draw it. So you could just copy it and then paste it into here and then evaluate it. And hopefully in a moment we'll see a pie chart. I don't see a pie chart. Oh, there it is. Okay. So that's an example of the sort of graphics that you can create. Sure, that'd be nice. And that's just an image that you can right-click on and save as. Okay, I'll say more about graphics later. All right, have a great weekend. See you later. Yes.
Question here. Error.
Yes.
For all the functions you guys declared here, then there's two arguments using it's one argument. I'm not sure what's going on.
Actually, this line that says out f.right. That's the one that's a problem. Right takes exactly one argument, but you've given it 2 arguments. You need to construct a string out of args and keywords.
Okay, okay.
So give exactly one argument to right. And it's annoying that the line number here doesn't match up with that. I haven't written the code to do that.
Okay.
That's
the project.
Yep. Yep.
Thank you.
So
Yes.
in our class, can we implement like a list to keep problem 3? I wanted to make a list of like possible coordinate inputs, and then like hopefully there could be a method that solves all the points in that.
Yep.
But every time I use a list, I keep getting an error that says get item not defined.
Okay, can I just see your code? It's probably just like some
I
little.
actually don't know.
It's on your project, right?
Yeah.
So just what's?
But I deleted some of it because I don't know why it wasn't working. But some of it should still be there.
Okay, what is your name?
Harsha.
How do you spell it?
Harsha.
Okay, I guess you haven't added me to your project, so
Oh.
it's kind of hard for me to see it.
I added
A lot of
A.
people-
Williamstein.
Oh, might be a different.
Okay,
If you add, the better thing is to add wstein@gmail.com because that'll uniquely
I'll
determine.
do that and then I'll
Yeah.
email.
Yeah, I'm not sure exactly what the email Simon also.
Thank you.
How do I upload something to the template for grades? I managed to confuse myself.
Template.
You know,
Sorry.
so I graded everything,
Yes, good.
and I don't know how to automatically make it submit.
Oh, you don't have to do anything.
Well, so in the top of the instructions
Okay.
it says, like, how will it know what the grade is?
Oh, we parse. So you have to do what it says there, but we actually read the file. We wrote a
Okay,
script that
so-
reads the file.
Do you have the grading worksheet?
Yeah. You mean the grading standards or whatever?
Yeah.
Yeah.
Just that
That's
tells you
here.
how.
Homework grading guidelines. Yes.
So then it has a link at the very top
Yeah. So,
that when I click that link, it says you do not have permission.
oh, that link is to this file.
Okay. So if you
I
want,
mean, it's literally exactly this file. So,
if you wanted to grade this file, I'd have to put homework total.
Yep. just in each of the homeworks that you graded, actually, that's not what it is. It says right here what to do. Put total x20 in a cell on its own. So just follow those
Okay,
directions.
just at the top, and I don't
Yep.
have to do it for each individual problem, do I?
Nope. All that matters is at the very top, it says total x/20, where x is like 18 or something. And then the fact that you can't read this suggests that you're not a collaborator on that project. So let me add you right now so that you can read it. So what's your name again?
Creek Jet.
Creek.
That's the last name.
Let's look. Jefferson Creek. Okay. Okay. Yeah, you were not on the project, and now you are.
Okay.
So
now I'd be able to read it. 'Cause I'm
Yeah.
not submitting anything that.
yeah.
Okay.
So the way I set it up now, if you're curious. Oops. See this directory? This is all of the projects of all the students, network mounted. So like when I do that, I just see all your files. So I just wrote a script that copies stuff out of there and copies stuff back there. So I just have like a little worksheet that's doing all the assigning and redistributing and all that.
Okay.
So that's why you don't have to do any physical submission.
Just edit it in our project.
Yep.
and pull it up. Okay.
Yep,
I'll
exactly.
make sure to put it properly in the problem.
Thanks. It makes it a lot easier.
Thank you.
Maybe outside, I have a question to ask you. So,
Okay,